Hello everyone, thank you for joining us today. I'm Mario Vázquez, Senior Software Engineer at Red Hat, and today we are going to talk about container security, an introduction to capabilities and Seccomp profiles. Let's get started. So first things first, what are Linux capabilities? Before jumping on what capabilities are, we need to understand that in Linux we have two types of processes. Privileged processes, whose effective user ID is 0, also referred to them as super user processes or root processes, and then unprivileged processes, whose effective UID is non-zero. Privileged processes bypass all kernel permission checks. On the other hand, unprivileged processes are subject to full permission checking based on the process's credentials, usually effective UID and effective GID, and also supplementary group list. Starting with kernel 2.2, Linux divides the privileges traditionally associated with superuser into distinct units, known as capabilities, which can be independently enabled and disabled. And those capabilities are a per thread attribute, meaning that every thread will have its own capability assigned. So if you look at the image in this slide, you can see that we have here a box with root. This is before the Linux kernel 2.2. At that point, root processes were assigned full privileges, and you cannot remove privileges from those processes. Then after Linux kernel 2.2, we have the same root process, but now we have different capabilities, which are the blue boxes here. So in this case, we can assign different privileges to the process. In this image, this represents that this process has the whole root privileges like it was before Linux kernel 2.2. And then we have this third image where we have the same root process, but now we only assign 3 capabilities in this case, which means that this process is only able to use those capabilities and not the other ones that were removed. So it doesn't have the whole root privileges enabled. Some examples of capabilities. Well, we have, for example, the net row, which will allow the process to use row and packet sockets. Then we have, for example, chown, that will allow the process to make arbitrary changes to file UIDs and GIDs. And there is a lot more of capabilities. There are like around 30 if I recall correctly. But anyway, at the end of the slides, there is a link where you can go and check the whole list of capabilities present on the Linux kernel as today. Why we talk about capabilities? Because sometimes we will need to use them on containers. And in fact, container runtimes already use capabilities. So for example, you can check the default capabilities enabled by Cryo on the link on the slides, and also the ones enabled by default by containerd on the link on the slides. So at the end of the day, as you know, containers are processes running on our system. So we can assign those capabilities to those processes which are containers. Default capabilities enabled by the runtimes are assigned to every container. If the user does not add or drop additional capabilities, all your containers will get the capabilities that are defined as default on the runtimes. Then one question that you will get during the presentation, which is, okay, how can I know which capabilities are required by my application? So there is no magic tool that will tell you which capabilities are actually required. The developer needs to understand what capabilities will be required by their application. For example, if we have an application that listens on port 80 and we want to run that application as a non-root user, which means a non-privileged process, we will need the netbind service capability, which allows a process to bind a port below 124 without being privileged, right? So that's something that the developer needs to know. There is no tool that will give you that information. Okay, so as you can see here in the screen, there is a bunch of text. There are 5 capability sets. I don't want to get into too many details. We will see how they work during the demo. You just need to know that those capability sets are used by the kernel to run some permission checks, and depending on the configuration of the different sets, your process will be able to get some capabilities or not. Then on top of thread capabilities, we have file capabilities, which are capabilities assigned to an executable file and that upon execution will be granted to the thread. The file capabilities are stored using 1 bit on the file system, but they act as different file capability sets. So they are not sets actually, but they work like if they were. And for file capabilities, we have only 3 sets: permitted, inheritable set, and effective set. You have seen those on the previous slide. As I mentioned before, we will see this in action. So let's go with demo 1, capabilities on containers. In this first demo, we are going to see how we can run a container locally and get its thread capabilities. So in order to do that, I will be using Podman, and as you can see here, we are running Podman, this image, and this image has an application that listens on a given port, but that's not important for now. We will be using this image during the demos. Okay, so now we have the container running. We can get the container PID using this command, podman inspect, and we can always get capabilities from the proc file system. So if we query cap on the proc the container PID status, we will get the different thread capability sets. If you remember, the inherited, permitted, effective, bounding, and ambient. As you can see, this returns the capability sets in X format, and we can use a tool named capsh to get them decoded. For example, let's decode the effective set in this case. Okay, so now you can see that this thread has the following capabilities: chown, DAC override, fowner, etc. etc. When using tools such Podman, we can also use commands as podman inspect and then get me the effective caps. Okay, that will be the same output. And with that, we conclude this first demo. But now what we are going to do is we are going to show the differences between running a container with UID 0 versus running a container with non-root UID. If you remember, we mentioned in these slides that there are differences between privileged processes capabilities and non-privileged processes capabilities. So what we are going to do in this time is we are going to run the same container, the same image using user 0, and using the entry point bin bus, we will run the grep command inside the container. So that will show us the thread capabilities for the container. Okay, so now we run this grep, and you can see here that we have the same capabilities that we saw before. Okay, and the important thing here is that we have those capabilities in all sets. As you can see here, those are in the inherited, permitted, effective, bounding. The ambient set, it's not set. Okay, so now we can exit the container, and now what we can do is run the same command, but this time we are using a non-root UID. In this case, we are using the 124 UID. Okay, so if I run ID, we are that one. Okay, if we run the same command, look at this. So we have all sets have been cleared, so all zeros, which means that we cannot get any capabilities because those are not in the inherited or permitted set. As you can see here in the bounding set, we still have the capabilities that were present on the privileged processes. The privileged process in this case has created this container, and that process had these capabilities. So those are in the bounding set as we have seen on the slides. Okay, so now we can exit. So what we can do now is we can run this same command, but at this point we are requesting this capability, cap netbind service. Okay, so what we are doing here is we are telling the container runtime that we want to be able to use this capability. What will happen then is that the runtime will put that capability into the ambient set. Sorry. Okay, so now we requested that capability, and if we run the grep command, you can see the difference. So we got the bounding set as before with the whole capabilities, but now in the ambient and then the effective, permitted and inherited, we got only the netbind service capability. So this means that this container can only use the netbind service capability. Okay, and now we can exit. Okay, for the next demo, what we are going to do is we are going to show a more real-world scenario, let's say. We mentioned earlier that our application can choose which port it listens on by the use of an environment variable. So what we are going to do is we are going to try to run our application using an unprivileged user on this unprivileged port 8080. Okay, so that works. Our application is listening on port 8080. So the next text that we are going to do is okay, we want to run this application but with an unprivileged user, but on a privileged, we want to listen on a privileged port number 80. And as you can see, we get a permission denied because we don't have the privileges to bind to that port. So what happened is that even if the runtime has the netbind service on the default capabilities that are assigned to containers, as you have seen in the previous demos, the capability sets get cleared when you run when you exec VE from a more privileged to a less privileged process. Okay, so what we need to do now is, okay, we know that we need netbind service. So what we are doing is we are running the same container, the same user on the privileged port 80, and we are adding the cap netbind service capability. So you can see that this time we were able to bind to port 80 because we have the privilege required to do that. Now let's move on to file capabilities. If you remember from previous tests, if you remember from the slides, we talked about something called file capabilities. So what are those file capabilities? Are capabilities that are assigned to executable files. Okay, so in this case, when we created our container image that we will be using, we used this command, seccomp, and then the capability that we want to add, the file capability that we want to add, and then in the effective and permitted sets, and the binary. In this case, this is the binary for my application. That means that my binary, when gets executed, will try to get this capability assigned to the application thread. Let's try. So again, we run this image, we are going to get the file capability. Okay, so we have this other command, getCap, where we can query the binary, and it will say, okay, this is the file capabilities that I have assigned. In this case, it only has netbind service. So as you can see, the thread capabilities at this point are cleared out, but we have the bounding set. If you remember from the slides, in the bounding set controls which capabilities can be added to the inherited and permitted sets. So if we run capsh decode, we will see that cap netbind service is right there, which means that a binary that has a file capability of cap netbind service will be able to request that capability. Let's see how. Let's run our application in background. Okay, so it's working, as you can see. and we got this PID number 5. So what we are going to do now is we are going to get the thread capabilities for this thread. And as you can see, this thread, the thread for PID number 5, only has this capability netbind service added to the thread's capability, because that's the one that the binary requested via the file capabilities. But at this point, maybe you can think that you can bypass capability checks, bypass thread capability checks. But let's see if that's possible, or if it actually it's not. So we have this command, podman run, same thing. We are using the same entry point and privileged user, and we are requesting the runtime to drop all capabilities. We are still setting the app port to port 80, and we are using the image that has the file capabilities. Okay, so if we look at the capabilities, now every set is clear, including the bounding set. If we run the get cap user bin reverse force, you can see that it has the file capability. So let's see what happens if we try to run this binary. Okay, the kernel blocks the execution. Why? Because the binary is trying to get that file capability into the thread capability, but the thread capability cannot acquire that capability because the bounding set is clear. So the parent process cannot create processes with those capabilities because itself doesn't have those capabilities in the bounding set. So can we bypass capabilities kernel checks? The answer is no. And with that, the demos around capabilities on containers are finished. We will see in the future how we can leverage capabilities on Kubernetes. Now that we are done with demo 1, let's continue with secure computing. So what is secure computing, or Seccomp? So applications usually require a small subset of the underlying operating system kernel APIs. For example, if we have an HTTPD server, it won't require the mount syscall at all, because why would the web server need access to run the mount syscall? So in this case, why should the app have access to this syscall? How can we limit that? So in order to limit the attack vector of a subverted process running in a container, the Seccomp Linux kernel feature can be used to limit which syscalls a process has access to. The previous example, we could say, okay, the HTTPD process can only use this subset of syscalls that I know that are required for the HTTPD server to run and nothing else. By default, Kubernetes runs everything as unconfined, which means that all syscalls are available to the containers processes. In Kubernetes 1.22, a new alpha feature will allow users to configure a default Seccomp profile that will be applied to all workloads otherwise specified, which means that you could have a default Seccomp profile that will be applied to workloads on your cluster, and then if you need something different, you need to provide a different Seccomp profile or run the workload as unconfined. In OpenShift, for example, we have a default Seccomp profile that will reduce the number of syscalls available for containers to use. But that profile is not applied by default to workloads. We need to say, I want to use that profile. Okay, so the next question will be, how can I create my own Seccomp profiles? And the answer is that creating Seccomp profiles can be tedious, and it often requires deep knowledge of the application. For example, a developer must be aware that a framework that sets up a network server to accept connections would translate into calling socket, bind, and listen system calls. So as you can imagine, that's not something very common. But there are some tools that can help you to get the syscalls that are being done by an application. For example, you have tools such as OCI Seccomp BPF hook that we will use in our next demo that will give us the syscalls being used by a process. Or you can also use tools as strace or BPF filters. There are many tools out there that you can get the syscalls being used by a process. Then there is another thing that you need to keep in mind, and is that when you're creating a Seccomp profile for containers, for example for Kubernetes, you need to keep in mind that you want to create that profile under the same container runtime that you are using in your cluster. For example, if you are using crun, you want to create the Seccomp profile using crun as a base. If you are running runc, you want to create the Seccomp profile using runc as a base. Okay, and now we have an example of a Seccomp profile, so we can see how it looks like. The first thing that we see is the default action. The default action will be the action that will be applied to syscalls that are not defined inside our profile. In this case, we are setting this to error, which means that syscalls that are not allowed in our profile will be denied. Then we have the architectures, which is the architectures that our Seccomp profile is targeting. And then we have the list of syscalls. We can have different groups, and we can have groups of allowed or groups of denied. In this case, having groups of denied syscalls doesn't make much sense because we have them here disabled by default. But we could set up the default action to log, which means that if a syscall is not defined in our profile but it gets used, it will be logged into the system that syscall was used. That will help us, for example, to improve our Seccomp profiles. Then, as I was mentioning, we have the syscall section where we have the names of the accepted syscalls that processes can use, and the action for those syscalls. In this case, we have 4 syscalls, and these 4 syscalls can be used. And as I was mentioning, we have 3 different actions that we can configure for our syscalls. The first one is allow the use of specified syscalls. The second one denies the use of specified syscalls, and the third one allows the use of the syscalls but logs the ones that are not specifically permitted. And with that, we got to demo 2, where we are going to see how we can use Seccomp profiles on containers. For the next demo, we are going to see how we can create our own Seccomp profiles using a tool which is the OCI hook project. Okay, so first thing first, we already installed the hook. You will have the instructions on the demo files. And what we are doing now is, one thing that is required is, in order to run this hook, we need to run containers as root. So that's why I'm using sudo here. So we are running our container, and we are adding this annotation to the container, which is called IO containers trace syscalls, and then we are giving it an output file, in this case tmp ls.json. We are running this Fedora 32 image, and we are running an ls on the root folder. Then we don't want to get any output on that command, so we are redirecting it to dev null. So let's see what happened. Okay, so the execution is complete now. So if we take a look at the ls.json file, you can see that in order to run that ls command, these are the syscalls that were used, all these ones. And the hook already created the Seccomp profile for us. So we can see that by default, any syscall that is not defined in there will be blocked, and that we only allow these syscalls to be used by our container. So what we can do now is we can run our container with this Seccomp profile. So we are saying, okay, security options, Seccomp, we want to use this profile, which is the one that we just generated. And we are going to run same image, same command. Let's see if that works. Okay, it works. So what's the next thing that we want to do? Okay, let's try what happens if we modify this command a bit. So let's run an ls-l. Okay, if you look at this, it says, hey, cannot access root, operation not permitted. So that's probably because we are missing some syscalls. So what we are going to do now is we are going to run this hook And we can do something really nice, which is, okay, now this is the input file, which is tmp.ls, and the output file, it's tmp.lsl. So what will happen is that all the other syscalls that we got from the first execution will be appended to the ones that we get now. This is really useful when you are testing your application, and for example, let's say that you have an application with 2 endpoints, and in the first execution you just tested one endpoint, and now you need to test the second endpoint. If for some reason the different endpoints require of different syscalls, this is an easy way of merging all syscalls in a single file. So we are executing this command again, and now if we run a diff between both files, we can see that for running the ls-l, we require these other syscalls that were not present in the previous profile. So what we are going to do now is using this profile, this new one, tmp.lsl.json, to run this application again. And now we can see that the application got executed properly. And that finishes the demo around Seccomp profiles on containers. What we will see in a future demo is how we can leverage these profiles on Kubernetes. Okay, now that we know how we can use capabilities and Seccomp profiles in containers in our local system, now it's the time to see how we can do the same thing on Kubernetes. Capabilities in Kubernetes have some limitations at the moment when not using UID 0 on your workloads, or what is the same when you're not running your containers with the user root. That's because the ambient capabilities are not supported in Kubernetes, but this will be solved in a future Kubernetes enhancement. In this case, user namespace can help, but at this point, support for user namespaces has made it to CRI-O, and it should be fully supported in Kubernetes in the next releases. Running containers with a fixed UID such as 0 has security implications. The processes sharing the same UID and with access to the same storage will be able to read and write the files from that storage. And also, if you can break out of the container due to a vulnerability, probably in the runtime, you will be able to see processes and files on the host owned by that UID. In those cases, tools like Linux will help reducing the attack surface in the node. While ambient capabilities make it to Kubernetes, we can use file capabilities or capability-aware programs. We will see that on the demo. On this slide, you can see the privilege escalation. There is a lot of text here, but you need to know that when you are using file capabilities or capability-aware programs on Kubernetes, you need those containers to be able to run privilege escalations, because you will be running a non-root process, and that non-root process needs to become a more privileged process. So that requires that privilege escalation. You have a lot more information around that in this slide. You can check it after the talk. And with that, we are going to see how we can configure capabilities on Kubernetes and the differences between running those containers on our local machine and running those containers in Kubernetes. Okay, for this demo, what we are going to do is we are going to see how we can leverage capabilities on Kubernetes. The first demo that we will be seeing is the difference between a pod running with UID 0 versus a pod running with non-root UID on Kubernetes. So first thing first, we create a namespace for our test. We are going to call it test capabilities. Okay, so we have our namespace created, and now we are going to create a pod. In this pod, as you can see, we are giving it a name, reverse words app cap test. So we are using the same image that we were using previously on the local test. We give it a name, and the container reverse words, as you can see, will be executed as user ID 0. Okay, we run this thing. And then after some time, we will get the pod running and we will be able to execute it. Let's wait a bit. Let's see how it goes. Okay, it's still container creating. Let's wait for it. Okay, now it's running. So let's try again. Okay, and now you can see that the capability sets are a bit different from what we have seen on our local execution. Let's decode them. So in this case, we have less capabilities than the ones that we had in Podman. Why? Because this is an OpenShift cluster and it's using Cryo under the hood, and those are the default capabilities assigned to Cryo, assigned by Cryo. Okay, so now what we are going to do is we are going to run the same image but with a non-root UID. So in this case we are running the container as user 124. Okay, so let's get the pods. Okay, it's running now. So what we are going to do is we are going to grep for capabilities, and here you can see the difference. In this case, since this container is running with a non-root UID, you can see that the permitted set, the effective set are cleared. In this case, you can see that the ambient capabilities are also cleared. That's normal because ambient capabilities are not supported by Kubernetes yet, so you will always get this capability set cleared. So if you remember from the slides, now that we have the ambient set cleared, that only leave us with two options. If we want to run an application in with a non-root UID that requires capabilities, and those options are just file capabilities or program capability-aware programs. Okay, so this finishes this first demo, and next we are going to see how we can run an application with NetBind service on Kubernetes. Okay, for this first deployment, we are going to run our application with root UID and drop every runtime capability but NetBind service. Okay, so let's create the deployment. So I will pause here. As you can see, we are running this container as UID 0, and now we are going to drop the capabilities that are assigned to every container by the runtime automatically. So in this case, we want to drop all these capabilities, and now we want to add NetBind service. That way our container will only have access to the NetBind service capability. Okay, and now let's get the logs for this application. As you can see, the application is listening on port 80, so that worked well. If we check the capability sets for this application, let's see what we get. Okay, so as you can see, we only got the NetBind service capability added to the different capability sets. That's expected. So what we are going to do now is we're going to drop all the runtime's capabilities again, and on top of that we're going to add NetBind service capability and request the application to run with a non-root UID. Okay, so let's do that. Again, I will pause on capabilities. As you can see, different things here. We are running as user ID 124, and now we want to drop the runtime's default capabilities as we did before, and now we want to add NetBind service. So at this point, the only difference between the two containers is that the former one is running with UID 0, and this one will run with a non-root UID. Let's see what happens. Okay, if we get the logs, you can see that we got a permission denied. Okay, at this point, you might think why it's failing, because we ran this test on Podman and it worked. But I will tell you something. In Podman, it worked because the ambient capabilities, if you remember, that ambient capability was the one allowing us to get that capability on the other thread capability sets, like permitted and effective. And this is not happening in Kubernetes because, as I mentioned earlier, ambient capabilities are not supported on Kubernetes yet. So what we are going to do is we are going to patch our application so we can access to it. We are changing the app port from 80 to 8080, and that will allow us to access the container. In this case, we want to get the capability sets. Okay, you can see that we have in the inherited set, we have the NetBeans service capability. Okay, and the same goes for the bounding set. So what are our options? Our options now are using capability aware programs or use file capabilities. So let's do that. What we are going to do now is we are going to patch the deployment again. We are setting the port back to port 80 and we're changing the image by the one that has our binary with the NetBeans service file capability configured. So let's do that. Okay, so that probably takes some time for the image to be pulled. So let me run get pods here. Okay, it's container creating. Let's wait a bit. Okay, the container is running now. So what we can do is we can get the logs. And you can see that now our container is listening on port 80. And if we check the thread capabilities for the process number 1, which is the process for our application, now we see that the permitted and the effective set got this NetBeans service assigned. So that is because when our binary was executed, the file capability was there and we had that capability in the bounding set, and that allowed the permitted and effective set to get that capability as well. And checking the capability on the file, on the binary file, you can see that we have this NetBeans service capability on the reverse words binary. And with that we finish the demo around capabilities on Kubernetes. And now that we have seen how capabilities work on Kubernetes, we're going to see how we can use Seccomp profiles in Kubernetes. By default, kubelet will try to find Seccomp profiles in the barlib kubelet Seccomp path, but this path can be configured in the kubelet configuration file. You can have multiple Seccomp profiles in the same folder, and remember that Kubernetes runs everything as unconfined by default. That, if you remember from previous slides, means that all syscalls are available for the processes to use. And in Kubernetes 1.22, as we mentioned earlier, a new alpha feature will allow users to configure a default Seccomp profile. And with that, let's see how we can use Seccomp profiles on Kubernetes. Okay, so in this demo, we are going to see how we can use Seccomp profiles on Kubernetes. So before we started with this demo, what I have done is I added a profile to my worker nodes. So I can run this command here, and you will see how one of my worker nodes has this profile CentOS 8-ls profile loaded on its barlib kubelet Seccomp folder, which is the default one, if you remember from the slides. So this ls profile, what allows us is to run the ls command, right, that we tested locally before. So what we're going to do now is we're going to create a namespace like we did before, and now we can configure the Seccomp profile at pod or container level. This time we're going to configure it at pod level, meaning that all containers within the pod will use this profile. So this pod, as you can see, is using security context Seccomp profile type localhost, because in this case we are using a local profile. We could use default and we would get the default OpenShift Seccomp profile that, as we mentioned in the slides, it restricts the number of syscalls that can be done. And this is the file that we are using, CentOS 8-ls. We are running this image and then we are running this command, ls on the root folder. So let's see what happens. Okay, it's been created. So let's see. Okay, we can see it's completed, and that it was able to list the different folders. So what we are going to do now is we are going to run another pod, but in this case we are running ls-l. If you remember, in Podman this failed. Let's see what happens in OpenShift. And also you can see that this time, instead of setting the Seccomp profile at pod level, we are setting it at container level, so we can have different containers using different profiles. Okay, so we created the pod, And now if we get the blocks, you can see that we get the same error that we got previously when we ran this demo on Podman. And with that, the demos around Seccomp are finished. Okay, so now that you have seen how you can use capabilities and Seccomp profiles on Kubernetes, the next question will be, okay, how can I manage capabilities and Seccomp on Kubernetes and OpenShift? In this presentation, we have been using capabilities and Seccomp without taking into account authorization for these resources and other stuff. In a real-world scenario, you want to restrict which user have access to what capabilities or Seccomp profiles. In OpenShift, we have security context constraint, or SCCs, that provides out-of-the-box standard security defaults, support for complex ordering, and those are enabled by default. In Kubernetes, we have pod security policies that can be used for controlling this as well, but they have a few drawbacks, like there are no defaults, you need to define them, the default ordering is not that good, then it's still not enabled by default in Kubernetes, so you need to enable it on the API server. They will be deprecated in Kubernetes 1.21, and the community is working towards pod security admission that will be the PSP replacement, the pod security policies replacement. You have the Kubernetes enhancement proposal on the slides. And with that, the talk is over. You have more resources if you want on the links on the screen. You have access to the live demos that we have done on the last link on this slide. And with that, if you have any questions, feel free to send them over to mario@redhat.com. And thank you again for joining us today. I hope you enjoyed the rest of DevConf US. Take care. Bye.